So in this topic, we have to really understand the structure and properties of giant covalent substances. And specifically, you have to know about the carbon networks that there are. We'll talk about that, carbon structures, and silicon, which we'll talk about briefly, and we'll talk about silicon dioxide or silica, much of which you'll remember from GCSE. So we're just going to go through those things now. These have covalent, this is language from the IB, network structures. We'll be calling that giant. We've been calling that giant covalent, haven't we, at GCSE, and that's fine. The language of the IB is covalent network structures. So let's make sure we get that, please. You will remember that carbon, you've just told me of our little starter, that carbon allotropes just meaning different physical forms of the same, or different structural forms of the same element in the same states as each other. So the other different solid forms of carbon, we've got diamond, which we need to know about, which we'll go have a look at in a second. Graphite, again we'll look at that in a second in a bit of detail. We need to know about fullerenes, and we need to know about graphene, all of which is GCSE. Right? You don't need to know any more than that. And again, we'll look at silicon and silicon dioxide in a bit. Let's just go through the key stuff, and because you've shown me already that you know that all the detail here, I am going to rattle through this fairly quickly. So diamond, you'll be clear that each carbon. So let's be clear they're all giant covalents. I'm not going to cover that every time. So let's do the general point first of all before we look at them in detail. These giant covalent substances are all going to have high melting points. This contrasts quite a lot from what we were doing last lesson, talking about intermolecular forces. We're talking here about if you melt these substances, these giant covalent substances or covalent network structures, you have to overcome all of the covalent bonds, the strong covalent bonds, which requires lots of energy. So we need to explain that here. So high melting points due to lots of strong covalent bonds require lots of energy to overcome. And it's rehearsing and practicing the kind of answers we kind of did at GCSE. Make sure you know that stuff still. It hasn't changed. The diamond, I'm sure you remember this, that each carbon bonds to 4 others. And that therefore means, we now know what this means, don't we? Because we've been talking about it when we're doing the shapes of molecules. Each carbon is therefore tetrahedral with 109.5 degree bond angles for all the reasons we talked about. 4 bonding pairs around each carbon, no lone pairs, electron domain geometry and molecular geometry, or the geometry around the carbons, are each 109.5 degrees. And that's what leads to its kind of very strong or hard properties. It's very hard material, isn't it, diamond? The hardest naturally occurring material to my knowledge. All right. Diamond's got high melting points for the reasons we talked about above, but it also doesn't conduct electricity. It's also got poor thermal conductivity. And the thermal conductivity we don't really mention at GCSE particularly, but I think that metals conduct thermal energy quite well because of delocalized electrons. And so both of these are explained by the fact that there are no delocalized electrons that can flow around, move around, and carry the charge or carry the thermal energy, right? So let's just remind ourselves of graphite. This time we've got a layered structure. And within a layer, you kind of got these hexagons of carbon rings. The key thing is that each carbon is bonded to 3 others. And we'll talk more next year about resonance and delocalized structures. I'm not going to do that now. There's no need to do it now. But you need to know really that because each carbon is bonded to 3 others in the layered structure, it means the result is, as you know from GCSE, that there are delocalized electrons. So one delocalized electron per carbon. Right. Delocalized just means not localized, not fixed in place. That's all it means. So one delocalized electron per carbon. And the thing about the delocalized electrons, as you excuse me, as you said a moment ago, is that electron, or those delocalized electrons, can flow through the structure through the layers specifically, so they only do conductivity through the layers, between the layers. So graphite conducts. Okay, so the electrons can flow and carry the charge. The delocalized electrons can carry the charge, and also because they can move around, they can carry thermal energy too. But again, just through the layer, just in one direction, rather than like metals where they can move all over the place. Right? Just going to pause for a sec. So graphene. Again, I know you know this from last year. This graphene is simply single layer of graphite. Everything's the same, except because it's a single layer, essentially a 2D molecule or 2D substance, and therefore is incredibly flexible, and it's strong for its size, for its thickness, incredible strength for its size, and of course it's extremely conductive. Those electrons that can flow on the surface of the graphene have very little resistance at all, so they're extremely conductive. For exactly the same reasons we've talked about before, the delocalized electrons, 1 per carbon, all that kind of stuff. Yeah. So I don't want to get into the detail of this now, and delocalization and all that kind of stuff, but you will learn next year about a substance called benzene. Benzene has got 6 carbons, a bit like the hexagonal rings, put this in brackets, a bit like the hexagonal rings you get in graphite. And those double bond, single bond structure, we'll learn that that's not a great representation of what's going on. In reality, this is drawn as a double bond, this is drawn as a single bond, drawn as a double bond, drawn as a single bond. In reality, those 6 electrons that are in the 3 double bonds there they're spread out over the whole structure, so we call it a delocalized system. So those electrons are swooshing around the outside. So in reality, those rings, you can think of them, for now at least, as a combination or a mixture of double bonds and single bonds. It's just that the double bonds can hop around, if you like, all over the place. That's a very noddy kind of version of an answer, but if you think of them as single bonds, that's not right. They're much more like having a double bond, double bonds in there as well, what we call pi electrons, but we'll explain all of that next year. Okay, that's not a great answer to your question, but it kind of gets you somewhere. It definitely does have full outer shells, but it's just treat it like it's a bit like a double bond. Anyway, so we've got fullerenes as well. And the fullerenes, again, did last year. We've got things like the Buckminster fullerenes. So those are those cage molecules. Now, technically, these are molecules. They're not giant covalent. But it's typically things like C60, but there are other versions as well. You can get C70. You've got these hollow structures, and those hollow structures can be used to potentially carry medicines around, and there's some other uses for them as well. They're actually can be used as lubricants because they can roll around, but they're spherical. Sure you remember that, and you may have been shown the architecture of Buckminster Fuller. Have everyone seen those pictures? Some people were shown those. So Buckminster Fuller was an architect, so I think in the early-ish 20th century, I believe. I might have got that wrong, but maybe early to mid 20th century. And you've got these kind of structures that look a little bit like Buckminster fullerenes, and these molecules are named after him or his architecture type. Buckminster fullerenes are molecules, they're C60 molecules, so there are intermolecular forces between the balls, but around the outside, they've got a structure a bit like graphene, sort of rolled up into a ball. So that's kind of how to imagine them, which means they conduct electricity around the surface, but not in bulk. So conduct electricity on the surface, but not in bulk. Because the electrons can't hop from one molecule to the next. And because they're simple covalent, compared to all the other structures we're talking about today, they have low melting points because they've got those weak London forces between the molecules. Okay, so weak London forces between molecules, which can be overcome quite easily. So again, very, very brief reminder of what you were taught last year, nothing more than that. But also within fullerenes, you don't spend all that long on this at GCSE, but you may remember learning about nanotubes. And nanotubes, just think of graphene rolled into like a hollow tube. So it's a bit like, this is my best description of it, hollow tube of graphene, you can think of it as. You don't need to know how they're produced, you don't need to know loads and loads about them, but you need to know there's different structural types, different allotropes of carbon, lots of them, that can be used for all sorts of interesting things. And I'll give you something to read on the uses of these things, much of which you've seen before, but in terms of what we need to know for now, that's basically it. But again, because it's graphene, they conduct. There's a similar structure to graphene, each carbon making 3 bonds and so on. They conduct electricity and heat, highly, highly conductive for the same reasons. They're incredibly strong for their size. So famous for strength, and used in all sorts of things. Strengthening, so used in things like tennis rackets and stuff, I believe. Very flexible and strong, all that kind of stuff. Right. So moving on a tiny bit from carbon, I want to remind you that silicon dioxide is silica. Structurally and property-wise, even though diamond is highly precious and expensive, and silica is not, silica is the stuff you get in sand and glass and so on, it's essentially structurally the same, so structurally very similar to diamond. So what you've got is each of the silicon atoms in a tetrahedral arrangement. I'll show you the notes come back up in a minute. But each of the silicon atoms, so I'm going to focus on this silicon atom here. If we ignore the white oxygens, each silicon is tetrahedral, and it would link a bit like diamond to 4 other silicon, but it does so through an oxygen. So the only difference there, we've got oxygens kind of in between each silicon. So it's structurally extremely similar to diamond. So therefore has the same, or largely the same properties as diamond. So high melting point, no conductivity, all of the same stuff. So properties very similar to. You won't be asked to draw it, but you're expected to know what silica is and that it's got a giant covalent or covalent network structure. Silicon also, you need to know a little bit about. I'm going to pause at that point. But you need to know that silicon, silicon is very similar to diamond as well. They're both in group 4 or 14 if you like, and therefore they have, you can say, similar stuff. So they've got the tetrahedral structure again, and all of that kind of stuff. But there is something slightly different. So I just want you to think about the silicon-silicon bond and the carbon-carbon bond. I want you to think about which of those would be the longer and weaker bond, and therefore which has the lower melting point. Carbon-carbon or silicon-silicon? Go. Point. So silicon atoms are bigger than carbon atoms. They've got a greater atomic radius. And so silicon-silicon bonds are longer and weaker. And so comparing diamond with silicon, you've got lower melting point. Lower melting point there. It's worth saying that all of these giant covalent substances, all of these covalent network structures have low solubility. And that wasn't covered at GCSE, but it might be useful to know now. And certainly it's sort of fairly obvious. I think you all know that graphite and diamond don't dissolve in water. Imagine if you dropped your engagement ring into the sea and it all dissolved. You'd be very upset about that. So fortunately that doesn't happen. I think so. That was a summary of what you need to know for giant covalent substances. We'll have a look at some questions in future lessons on this, but you need to know the detail of those things, and I'll share some slides with you. That's it for that one.